Center for Marine Remote Sensing with Dr. Franklin. I am hosting our guest today with Natasha Mendez, who is also a PhD candidate working under Pamela Carter.
No.
Helen Miller. Oh my goodness.
It's my little brother, you know.
We'll get over this one. I'll get it right from my teacher.
No, we introduce you. Sir Franklin.
So, Dr. Edwin Hernandez is a he has his PhD in tropical biology with a specialization in coral reef ecology, and he did a postdoc in molecular microbiology of coral diseases. He has been an affiliate researcher for a while now at the Department of Biology at the University of Puerto Rico. He is also a research fellow at the Center for Applied Tropical Ecology and Conservation at the university, where he coordinates the Coral Reef Research Group. He has been a principal investigator at the Marine Environment Society, Sociedad Ambiente Marino. And we have a couple of students here that's been from there. And Natasha will talk about the type of work he does.
So at the present, Dr. Hernandez coordinates various components of several projects of the community-based, wait, no, I'm confused over here. So many titles and so many organizations. For the Center for Applied Tropical Ecology and Conservation at the University of Puerto Rico and the Sociedad Ambiente Marino that Maria just mentioned. Regarding coral farming, coral reef rehabilitation, marine mitigation of environmental impacts, and coral reef cross-scale research activities associated to coral demographic dynamics, local anthropogenic and climate change long-term impacts on coral reef population, community and ecosystem dynamics, impacts of land-based source pollution and coral reef recovery dynamics, and coral farming and reef ecological rehabilitation. So those who know me know I'm pretty excited about coral, so I am really happy to have Dr. Hernandez over here. So the presentation will go for about 40 minutes. Please hold your questions until the end, and without further ado, we'll leave you with Dr. Hernandez and his presentation titled Coral Reef Community Trajectories in a Climate of Change, Cross-Scale Implications for Persistence and Resilience.
Gracias. First of all, thank you so much for the invitation. I'm really thrilled that I was able to make it finally to USF. I will try to speak a little bit about some of the projects. I don't know if you can hear me clearly back there. Good. If I overextend speaking, just show up a beer. You will remind me that I have to finish. Sometimes I get involved into the things that I'm talking about. Why it became black? Did I hit something wrong here? Oh, there you go. Okay. Yeah, we'll learn a little bit. Basically, I will start talking a little bit about where I come from. I'm a coral reef ecologist at the University of Puerto Rico. I work for the Center for Applied Tropical Ecology and Conservation. I'm also a lecturer at the Department of Biology. At UPR Rio Piedras, people tend to think about the Marine Sciences Department of UPR, which is in the Mayagüez campus on the other side of the island. We do have some coral reef research components at UPR, Rio Piedras campus, which is in San Juan. And I'm the coordinator of the Coral Reef Research Group. CATEC, which is the acronym for the center, has different components, terrestrial ecological components, genetical ecology, some molecular components, etc., regarding conservation in the neotropics. And since 2007, the first cycle of funding from NSF got established dealing with the terrestrial component, and then I got the invitation to join them. That's when my life kind of changed. I switched from a data collection expert into a scientist, as my boss said. Basically, we're focused on different components of reef research, like the long-term impacts of climate change in reef ecosystem, and also I work with different anthropogenic stressors like sewage, sediments, turbidity, fishing impacts, etc. We also have some studies dealing with the acclimatation responses of corals and population dynamics, especially focused on ESA-listed coral species like acroporids and also Orbicella. And the other thing that Maria and Natasha mentioned, we work with the coral components of coral farming and restoration impacts on ecosystem functions. We are not only focused on the coral dynamics once we place them back to the reef, but also what happens in terms of fish recruitment, fish community structure, herbivory, etc. And the other element that we are working with is land use changes and the impact of terrestrial marine connectivity in the, over longer time scales on adjacent coastal habitats. And finally, the Caribbean paleoclimate dynamics, looking at sclerochronological tools as recorders of climate change. I'm not going to talk about all of these things, but just to give you an idea of the kind of things that we have. I will try to address these 4 principal topics today. We'll start talking a little bit about some cross-scale drivers of coral reef decline in the northeastern Caribbean, some case studies from Puerto Rico, from the things that we have been doing. Some of that has been published, some other stuff not yet. What are the implications of these trends of changes that we are looking in coral reefs? To make the story short, basically one of the most significant components of change has been the threats that reefs are getting, no? Just because of the increase in atmospheric carbon dioxide concentration. So we have hit already the 400 plus parts per million benchmark, and we have been moving around. I think it's 399 or something like that the last time that I look at the data set. But basically, if we look at those major threats like sea surface warming, acidification, hurricanes, and sea level rise, all of these produce a combination of impacts that some of them actually interact together, like warming produces bleaching that can have as a consequence a decline of reef building species, and I will address that aspect later in my presentation. And this has like a cascade reaction in terms of producing a declining biodiversity or a loss in species richness, especially in reef building taxa, in the large reef building taxa like Orbicellas, etc. Those reefs that die, or those corals that die, become dominated by macroalgae in the long run, and especially in areas subjected to water quality decline, there's an increase in bioerosion rates. So basically what we're looking is like a decline also, not only losing the biological component, but you start losing now the structure in some of these areas. And when you have these other components, it will drive the system into declining calcification rates. Hurricanes can also have a physical impact and losing microhabitat structure, etc. And the whole end product of all of these processes together is an ecosystem resilience decline, okay? So the system doesn't have an ability to bounce back from disturbance, and that's when things get tough in the reef. I'm not drunk yet, so. Jesus. I'm hitting the same button and it's stuck all of a sudden. Okay, there you go. No. Okay, I need more beer then. I'm getting recorded forever on the internet, drinking. So when we start looking at disturbance on coral reefs, we got to realize that disturbance is something that we need to measure in terms of the spatial scale. So when we think about the coral reef scale, which would be like the ecological scale, but there are some components that will have impacts across increasing spatial scales from local habitats. And when we think about local, you think about stuff like fishing sewage, sediments, turbidity, military impacts in the case of Puerto Rico. And you have like land-based source pollution impacts, etc., land use changes. But then you start getting to larger spatial scales, and you have some events like extreme rainfall events. And in Puerto Rico and the northeastern Caribbean region, there has been a consistent trend in decline in overall rainfall, and we have been in a drought over this year because of El Niño and the changes in atmospheric circulation. But the frequency of extreme rainfall episodes, those very small scale but very strong supercells, and we have rainfall events all of a sudden, like 10 inches of rain just in a single event, and an increase in the frequency of these events across the northeastern region. Across the mesoscales, we got increases in sea surface temperature. Probably if you get to regional scales, you got changes in the North Atlantic Oscillation. And when you look at the North Atlantic Oscillation Index, we'll talk a bit about that a little bit later. And then you get to global scales, like changes in atmospheric temperature and dissolved and CO2 concentrations. So when you look at those processes, you can actually split them into type of wide categories. One of them will be like stochastic changes. A hurricane can be an stochastic event that can probably destroy an area, and reefs have the ability to bounce back from such kind of disturbance, but depending on where you are and what is your environmental history. Because under normal conditions, a reef can be smashed like a forest by a storm, and it can bounce back in a given time scale. But when you have recurrent disturbances, like from those other things associated to gradual changes, if you have a chronic problem of water quality condition, then you have probably a recurrent frequency of pulse events so frequently that it becomes a chronic problem. Then those kind of disturbances, it takes longer for the reef to repair those kind of damages. So the time frame necessary for recovering from this disturbance to this other one, you will require more time to recover from that other disturbance, and so on. So those stochastic changes that the reef had the normal condition to recover, now you have a problem. And for example, the Diadema die-off, we still have a lot of reefs, and places that are supposed to be pristine reefs, like Mona Island, halfway between Puerto Rico and the Dominican Republic. And the last time that we ran, I don't know how many, couple of hundreds of transects, only 8 Diadema individuals across the entire Mona Island shelf. So that tells you a story. This is a place with a 200-foot visibility most of the time underwater. But no sewage, no nothing, but we have a major disconnection just because of the oceanographic conditions there. So that tells us something is going on. Disease outbreaks, massive bleaching events, etc. Those are examples of stochastic change. But there are some things that normally most jurisdictions fail to address, which are those gradual changes. Just because they are not, at least in Puerto Rico, there has not been a very well thought and a very well coordinated long-term monitoring component of changes in coral reefs. Most of these changes, we have failed to look at those changes. Now we have a problem that the reef is changing so much, and we don't realize what's going on. And if we go back to history, we got to address this in a longer temporal scale. It's not only from the last couple of decades, but when we go back to the colonization times. The Spanish went to Puerto Rico for the first time in 1492. And there's a history of major deforestation that started around the island in the 1600s, first for cattle growth because of, at that time, leather production, then subsistence agriculture, then expansion of urban areas to the higher mountains. And for us, a higher mountain is not higher than a 1,300 meters or so. Expansion of sugar cane, especially over the mid-19th century. and then an industrialization of the sugarcane industry early in the 20th century. And then we had what was called the Operation Bootstrap. Once Puerto Rico became part of the United States, formally as a Commonwealth, 1952, there was a major change in the type of development, and we basically switched from agricultural to industrial. And that's when all of these major urban sprawling highways, sewage plants, etc., start to be constructed, and that's when the things start changing. This is Puerto Rico in concrete. You remove the island, you can still see the island. We have over 26,000 kilometers of road in a 100 by 35 mile long island. And if we were to build a road, I would be able to see my good friend Austin Bowden Kirby in Fiji. That's 26,000 kilometers down there. That's the kind of roads that we have in Puerto Rico. So that's something significant for such a small island. And that's the way Puerto Rico looks. That's only 4 examples of what the shoreline looks at some places which there's a lot of development going on, especially across watershed scales. We have not been very good in trying to have some controls of sedimentation and erosion along watersheds, and that has a very high price for adjacent coral reef habitats. We got many places that look like this, and there's a reef there, if you can believe me. But the frequency of these conditions like disease or coral syndromes increase with declining distance. I mean, the closer you are to the problem, the more frequent you see these kind of conditions. And even in some areas that are kind of offshore, you have major algal blooms that are literally overgrowing corals. And the whole idea is that when you look at these transition mechanisms, you can split the reef in 3 basic general conditions. You got these highly resilient reefs, which are characterized by very high diversity, very nice coral cover, moderate to very high spatial relief, a large cover of crustose coralline algae, which is the type of bottom that coral spat used to recognize for recruitment, etc. But then different kind of disturbance can drive you to different transitional stage where you have a declining trend in all of these parameters that I mentioned. And if you have additionally factors like hurricanes, etc., or any kind of local chronic condition of sediment, then you have a major decline in any of these elements that I mentioned before. And when you look at the composition of coral communities, basically under those highly resilient conditions, what you have is a reef that is basically dominated by competitive, stress-sensitive taxa. But when you get into transitional stages, then you have like a rapid decline in those particular corals. Then you have like stress-tolerant corals tend to dominate the reef, and you have an increase in those weedy ephemeral taxa that are also taking over the opportunity, you know. And when you have those collapsing reefs, you basically get rid of most of these stress-sensitive corals, and you start looking at the decline of those stress-tolerant corals, and the weedy species take over. And this pattern, I'm going to talk a bit in a few minutes about this in particular, because this is the change that we are looking at recruitment, in coral recruitment right now in these days on most of the areas. So this change, what we see is a decline first in the persistence of the system, and eventually in the resilience, in the ability to naturally bounce back from that disturbance. And it's because a combination of human-driven factors, but also some natural factors that have been always, there has been always hurricanes, there have been always reefs, but the combination of these natural impacts of already stressed systems creates a major change in what happens in the reef. What is the particular nature of the Caribbean in comparison to other areas in the planet, like let's say the Indo-Pacific or the Great Barrier Reef, etc., is that we have a very low functional redundancy. If you take the case of the acroporids, You go to the Indo-Pacific, they have what, over 130 at least species of acroporas. You get to the reef, you get next year, and you might have probably lost about 10 species that you don't even notice, because immediately you lost them, immediately there's a recruitment by another species and can take over that function. But if you go to the reef here and you lose our single reef building acroporid for the very shallow areas, which is Acropora palmata, you have a trouble because you don't have a substitute for that particular type of coral. And the same happened with staghorn. So that's a problem for the Caribbean, because the impact of losing one species is highly magnified in comparison to losing that same one species over other areas in the planet. The other aspect of these small population sizes is that in the long run, if you have a lower amount of these corals, you got like a genetic isolation problem, and you got alley effects. So you can still have some reproductive individuals, but they are so far away from other individuals that the possibility of having a sexual recombination and sexual recruitment is very low for many areas. And the other aspect is that for taxa like Orbicelas and that kind of large star corals, when you have a rapid population decline in those massive corals that are characterized by very low recruitment rates, there's basically a permanent recruitment failure for many of these species. And long-term recruitment data from many areas like the U.S. Virgin Islands, etc., show that virtually no recruitment or very low recruitment rates for these corals. And the same for us when we started looking at recruitment of these coral species over 8 years ago. Recruitment has been non-existent, at least on the areas that we are working. The other threats to persistence and resilience, we got to look at some examples. Those are from coral cores from the eastern coast of Puerto Rico, close to the Fajardo River in northeastern Puerto Rico. Oops, I hit something here. Sorry. There you go. Coral growth is vulnerable to land-based source pollution. This is a graph of coral skeletal linear extension in Orbicella annularis for Fajardo, and this is annual stream flow